Welcome. In this video, we'll be going over the stability of circuits that have feedback. So let's get started. So we'll be looking at the stability of feedback systems. And we'll first mention that there's a control theory, an area of control theory, that generally deals with a system or a plant, as they sometimes refer to it in control theory, the system that starts off as being unstable. And then they add feedback and a controller to this system, and they make the overall system stable. So that's control theory. That's not what we're going to be dealing with. Here, because we're dealing with circuits, we start off with a stable circuit, generally speaking, and such as an amplifier. But then we add feedback around to get some benefits of the feedback. So we've seen before that benefits of feedback are improved linearity, improved frequency response, improved port impedance, and improved gain sensitivity. So we'll be adding feedback not to stabilize the system because it's already stable, but to get some of these other benefits of feedback. Now it turns out though, we start off with a stable system. However, when we add our feedback, we need to ensure that the new circuit remains stable and it has a good settling behavior. And so we'll see that we'll use some phase margin and other techniques in order to quantify how stable it is and what the settling behavior might look like. So let's talk about, in general, what the poles are for a linear time invariant system. So I want to look at the poles of a linear time invariant, so LTI system. So this would be the closed loop. This would be a circuit that has the feedback already put around it, and this would be the entire system then. So if we assume just an arbitrary nth order LTI system, and we no longer, up to this point, we were assuming that all our poles and zeros were on the real axis. That's no longer the case. We're no longer making that assumption, so our poles and zeros can be complex now. So if we assume we have a linear time invariant system, H of S, we have an input U of t and an output Y of t coming here. So we can write H of S in polynomial form, and that's written as this equation here, which would be the numerator. It's an mth order, so it has order m for the numerator polynomial, divided by an nth order, so an order n for the denominator polynomial. And this would be called polynomial form. So this is polynomial form for the first equation. But we can also write the same transfer function in root form. And that would be shown here, where we can divide through this a sub m and b sub n, put them and pull them out of this equation, and then have all our roots, s minus z1 times s minus z2, s minus z sub m, and so on. And all the poles, which are s minus p1, s minus p2, all the way to s minus p sub n. And recall that the numerator has an order m, whereas the denominator has an order n. And this is our root form here, equation 2. So what we find is that in root form, our zeros are at z sub I. So in other words, the transfer function here, h of s, goes to 0 when s is equal to z1, also goes to 0 when s is equal to z2, or when s is equal to z sub m. So in each of z sub I, the zeros occur for the transfer function. We also say it has poles at p sub I because h of s goes to infinity when s is equal to p1, or when s is equal to p2, or s is equal to p sub n. So those become the poles of our system. Now for a general arbitrary transfer function, z sub I and p sub I can be complex. However, if all of the a sub I and b sub i's, so if we started off having a real polynomials up here. So this also, all the a sub i's here were real, and all the b sub i's in this equation are real. So for a real input, we get a real output. Then you can show that all of the z sub i's and p sub i's, if they're complex, they must occur in complex conjugate pairs. What does that mean? If you go back to your math days, we can see that a complex conjugate is if we have a complex number, which is written as sigma 1 plus j omega 1, where both sigma 1 and omega 1 are both real values, then the complex conjugate of z will be sigma 1 minus j omega 1. In other words, the complex conjugate is really just changing this plus sign to the minus sign. If it was already the minus sign, obviously, if omega 1 was negative, then it would become a plus sign. So anyway, it always changes the complex portion, takes the inversion of that. But the real part remains the same. So in the case of complex conjugate pairs, if p sub I happens to be sigma I plus j sub omega I is a pole, then p sub I complex conjugate of p sub I must also be a pole. So sigma I minus j omega sub I would also be a pole. And the same thing would be true for the zeros, because the zeros will also occur in complex conjugate pairs. So if z sub I is a 0, then z sub I complex conjugate must also be a 0. Now that's not the case if it's real. So if we have a pole which is just a real value, so p sub I is a real value, then it does not have to have a pair. So there's no complex conjugate there. We can have a single real value, or it could be, we can have two real values at the same point, but they don't have to occur in pairs the way they do for complex conjugates. So when they're actually complex, have a complex part to it. Now for this transfer function here that we have shown in either polynomial form or in root form here, we'd like to know, how do we know if it's stable? Well, for h of s to be stable, two things have to be true. N must be greater than or equal to m. So the order of the denominator must be at least equal to the order of the numerator or higher than the order of the numerator. You can see this because if the order of the numerator is less than the order of the denominator, then as you go of s equal to infinity, the gain at infinite frequency would increase and would go on to infinity. So you must have a gain which does not go to infinity at infinite frequency, or infinite s. Also, all your poles must be in the left half plane. So in other words, all of the real part of the poles must be negative. And that will result in a stable h of s. Let's look at some examples here. So here's an example of some stable poles. So we're going to look at three h of s's. And we'll look at the step response for all three of these h of s's. So the first one is just going to be h sub 1 of s. And that's 1 e to the 6th divided by s plus 1 e to the 6th. So this has a pole at negative 1 e to the 1 e to the 6th, so negative 1 mega radians per second. It has a DC gain. When we let s equal to 0, we'll see that the DC gain is just the numerator divided by the constant down here, so the DC gain is equal to 1. And so I plot the poles on the s-plane. So this would be the s-plane shown here. And s is equal to sigma plus j omega. Then we have that the pole in this location would just be a single pole at minus 1 e to the 6th. The second transfer function we want to look at is we'll place two poles at 1 e to the minus 6. We'll call that h sub 2 of s. In this case, the numerator is 1 e to the 12th, And we'll divide this by s squared plus 2e to the 6 times s plus 1e to the 12th. If you take the roots, if you put this into MATLAB and you find its roots, you'll find that it has two roots, one at minus 1e to the 6th and another root at minus 1e to the 6th. So it has two poles at minus 1e to the 6th. And the DC gain, again, when s is equal to 0, is 1e to the 12th divided by 1e to the 12th, so the DC gain again is 1. Now the third example, then the S-plane for this is just two poles at minus 1e to the 6th. So a pole and another pole at minus 1e to the 6th. The third example, you want to look at complex poles. So third example is h sub 3 of s, which is given by this numerator divided by this denominator. And again, if you take the roots of this, you put that into MATLAB, you'll find that its roots are minus 1e to the 6th plus or minus 10e to the 6th times j. So we have that, and the DC gain again of this will be the numerator divided by this portion here, because s is equal to 0 for DC gain, and so it's also a DC gain of 1. And if you plot the S-plane plot for this, you'll see that you have a pole at minus 1e to the 6th plus 10e to the 6th times j. This is the j omega axis. And also another pole at the bottom side. So it's minus 1e to the 6th minus 10e to the 6th times j. And just another value to note here is T3. We'll look at this value here. And that will be equal to 2 pi divided by 10e to the 6th. And where's this coming from? Because of this value here, omega is equal to 10e to the 6th. Remember that omega equals 2 pi times f. So f is equal to omega over 2 pi. So this t is the period of this frequency in hertz. So 10e to the 6th divided by 2 pi is the frequency in hertz. And this would be the period of that. So the period of this frequency in radians per second, shown here, is equal to 0.628 microseconds. Now if we plot the step responses for all three, we get a curve that looks like this. So we see H1 is shown here. It's the blue line, which just comes up like that. H2 is shown here. H2, recall, has two poles at minus 1e to the 6th and minus 1e to the 6th. And so the step response for that looks like this curve, which is the red curve here. And notice our timeline is times 10 to the minus 6, so this is in microseconds. And finally, the last one here is H3. It's shown here, and it has poles at minus 1e to the minus 1e to the 6th plus or minus 10e to the 6th times j. And that has a step response that looks something like this. So you can see that step response for this last one is ringing quite a bit. And that's because it has a very large complex part relative to its real part. So it has a lot of ringing in this case. So it's stable. How do we know it's stable? If we look at the amplitude of its ringing, it's just decaying down towards 0. So it's settling out. If you also notice that the amplitude, if you look at the H1 term here, we see that it also shows exactly the dampening of the ringing part for H3. So the real part of H3, it's exactly the same as the real part for H1 of S, shows how it's decaying and it's stable. But we do get a large ringing part for H3 of S. Now, let's do the similar example, but we'll have unstable poles now. So in this case, H1 prime will be 1e to the 6th, but times S minus 1e to the minus 6th. S minus 1e to the 6th. So So the difference is we have a minus sign here, whereas in the first case we had a plus sign in just H1 of S, the previous case. Similarly for H2, we have changed this to be a minus sign. So this makes our poles in the right half plane. And similarly for H3, we have a minus sign over here. And so if we look at the three, the pole locations, we now have the poles in the right half plane for H1. We have the poles in the right half plane for H2 prime of S. And we have the poles again in the right half plane for H3 prime of S. So they're the same location, a mirror image of what they were before. So they're in the right half plane, but 1 e to the 6 rather than minus 1 e to the 6. And we put a step response into that, we see this result shown here. So we can see that H1, just shown here, is now growing forward in time, and it will grow towards infinity. H2 grows even quicker because it has two poles at the same location in the right half plane. It's growing even faster than H1. And finally we have H3, which is ringing again and having the amplitude growing at the same rate as H1. So that's H3. So all three are now unstable because our poles are now in the right half plane. And so a step response into it causes it to grow without bounds. Now, same would be true of an impulse response or any other disturbance. So as long as the states do not start off all at 0, it grows without bounds, and we call that an unstable system. Our final example we want to look at is when our poles are exactly on the j omega axis. So in this case here, we'll have H1. Actually, we'll have H1 given by this equation, 1 e to the 6th divided by s. H2 double prime, sorry, that was H1 double prime. H2 double prime will be 1 e to the 12th divided by s squared. And H3 double prime will be 1 e to the 12th divided by s squared plus 100 e to the 12th. Sorry, this is 100 e to the 12th divided by s squared plus 100 e to the 12th. And so if you look at this, we now see that for the first case, H1 double prime, we have our pole at s equal to 0. For H2 double prime, we have our two poles at s equal to 0. And for H3 double prime, we have poles at plus 10 e to the 6th j and minus 10 e to the 6th j. So in all three cases, our poles are directly on the j omega axis. And now we'd like to look at the step response for those three cases. If we plot that, we'll see this result here. So for H1, it grows because a step response is 0, 1, and then just stays 1 for all time. It's integrating it. So it's integrating at a certain rate, and we see it just growing without bound. So that's an integrator. In H2 double prime, there's two zeros at s equal to 0, so it's a double integration, and we see it growing quicker than H1 double prime. But if we look at the last case, which is now H3 double prime, we see for a step response, we get our ringing that we saw before, but it's not growing. It's just remaining at the same value. So it's actually remaining at a constant amplitude and not increasing or decreasing. If the pole was in the left half plane, it would be decreasing. If the pole is in the right half plane, it would be increasing. But if it's directly, if the pole is exactly, the real part of the pole is exactly 0, and it's not, and there is a complex part to it, then we'll see this ringing part. But it doesn't increase or decrease. And the one thing I should have mentioned earlier is if we go back and we look at this period of the ringing, so T3 here, that period, it's exactly what we saw up here. T3, the period of this is exactly 0.628 microseconds. So it's determined by the omega portion of this. So when we looked at our poles, we had our pole at plus or minus 10 e to the 6 times j. That determines the period here, T3, of our ringing part. And it will also determine the period then of our oscillator. And in this last case here, this would be an oscillator, and the period here again would be just T3 from here to here. So our last case here is a way of building an oscillator. So this is just in general looking at any linear time invariant system that has possible complex poles. So I want to look at the poles of a closed loop feedback system. And so what we just saw above is that the poles of a system determine the stability and the settling behavior of that system, how quickly it settles, and the oscillation frequency that it may ring at. Now you can also show that the poles of a system don't depend upon where the input is applied or where the output is taken. So you just need to look at the poles to determine if it's stable, unstable, or what the step response ringing will be, an overshoot, and how long it will take to settle. Now the loop gain, which we've seen before when we look at feedback systems, turns out we can use that to find the poles of a system that has feedback. So if you recall, we found that the closed loop gain of a feedback system was equal to a sub L infinity times L of S divided by 1 plus L of S plus a sub L naught times 1 divided by 1 plus L of S. So what we see here is that the poles of a sub CL, of the closed loop system, a sub CL of S, is equal to the roots of 1 plus L of S. So the poles of the closed loop system are where 1 plus L of S is equal to 0. In other words, that's where a sub, the closed loop gain, goes to infinity. Now, recall that in feedback circuits, and the key here is saying circuits, not feedback systems, but feedback circuits, all the poles of L of S are real axis poles. So we refer those as the open loop poles then. So we say that the open loop poles, which are the poles of L of S, they're all real axis poles. Whereas the closed loop poles are the poles of 1 plus L of S. So the root, I should say the roots of 1 plus L of S. Sorry, that should say the roots here. This here should say the roots of 1 plus L of S would be the poles. So the poles of A sub CL of S. So now let's look at the case of a first order L of S. And if we had feedback in it, how does that affect things? So if we have L of S is equal to L naught divided by 1 plus S over omega P, we say our open loop pole is at minus omega P, and L naught should be greater than 0 for it to be a stable system, for it to be negative feedback. Otherwise it would be positive feedback. So we have that the 1 plus L of S is equal to 0 is the pole of the closed loop system. And so we can write that out as 1 plus, so if we take L of S and substitute that in here, it's equal to 0, so we can multiply the left and the top and the bottom by 1 plus S omega P. We end up with this equation here. 1 plus S over omega P plus L naught is equal to 0. We can solve for S, and we end up that S, which is the root or the pole of this system, is equal to minus 1 plus L naught divided by, or multiplied by omega P. So the closed loop pole is at minus 1 plus L naught times omega P. And I can refer that as minus omega P prime. So this is the closed loop pole here, whereas our open loop pole is equal to minus omega p. So what we see then is that we started off with a pole in the negative left half plane because the pole was at minus omega p, and we ended up with a pole still in the negative left half plane, but multiplied by 1 plus L naught. So in other words, we started with a pole in this location and it moved to this location here. So it's always stable no matter what we have as our L naught. So for a first order system, we don't have to worry about it being unstable, except for making L naught greater than 0, or sorry, making L naught less than 0, which would make positive feedback rather than negative feedback. But ignoring that possibility, we will always have a stable system if we start off with L of S being first order. So now let's take the case of L of S being second order. So now L of S will be shown as this, L naught divided by 1 plus S over omega P1 times 1 plus S over omega P2. And again, we'll assume that L naught is greater than 0. We'll assume that omega P1 does not equal omega P2. And so we would say this has the open loop poles of this system, or the open loop, or the poles of L of S, which are minus omega P1 and minus omega P2. Now we can show that if we put this into 1 plus L of S equal to 0 and find the roots of it, that as L naught is increased, so for L naught equal to 0, the poles would just remain at these two locations here, the original first locations. But as we increase L naught, these poles move together like this, so they move towards each other, they meet, and then they split and go up and down. So they actually will end up, as you increase L naught, they could end up somewhere over here in the complex part. So you could start off with two real axis poles, come together, split, and end up with complex conjugate poles. This is the S-plane that we're showing here. So what we see is that as L naught is increased, the poles come together and split into complex conjugate poles. So what we see is that it always remains stable, but could have a lot of ringing as the poles move away from the real axis. The further they get away from the real axis relative to the distance along the real axis they are, the higher the ringing is going to be. And we saw a lot of ringing in the example that we saw. In that case, our complex part was 10 times higher than our real part. The third example we want to look at is also a third order case, and it's L of S is equal now to L naught divided by 1 plus S over omega P1 times 1 plus S over omega P2 times 1 plus S over omega P3. In this case, you can show that as L naught is equal to 0, you end up with essentially with these three poles here. But as you increase L naught, these two poles move together, and this pole moves to the left. And then they could split and come out across here, and this would just keep going to the left this way. So as L naught increases, you could end up with these three poles over here. And if L naught keeps increasing, you could end up with poles that end up in the right half plane over here to the right, and you'd have an unstable system. So in this case, for the third order system, as L naught is increased, our poles go into the right half plane, and we end up with an unstable system. So we need some method to figure out whether our closed loop system is going to be stable and how stable it's going to be. Now, we won't always have L of S available to us. What we'll have if we're running a simulation is we can plot the magnitude of L of S and the phase of L of S. But actually finding the values for L of S is often quite difficult and not easily done. If we have 20 or 30 transistors, there could be many different poles and so forth. So fortunately, it turns out that we can use something called phase margin and gain margin that will study the stability for a closed loop system. So we'll make use of that going forward. So we need to discuss what is phase margin and gain margin. So this is based upon the magnitude and the phase of L of S. So what we do is we plot the magnitude of L of S, and we plot the phase of L of j omega. So I said the magnitude of L of S, I should have said when you plot the magnitude of L of j omega and the phase of L of j omega. So if you plot those two together, we end up with a plot that looks something like this, where the top here is the magnitude of L of j omega in dB, and the lower curve is the phase of L of j omega in degrees. And we define two frequencies. We define omega 1 to be where the magnitude of L of j omega 1 is equal to 1. So in other words, visually, wherever this curve here crosses 0 dB. So that should be have a 0 over here for 0 dB. So this becomes omega 1, and that's our definition, where the magnitude of the loop gain becomes 1. We also defined another term. That's where the phase of the loop gain is equal to minus 180. So where the phase, which is shown here, crosses minus 180, and so we'll define that as omega sub 180. So we have omega sub 180 given by this equation here. So we define two frequencies here. Now once we define those, we can define what phase margin and gain margin is. And if you notice, we plotted the phase here in degrees on the left-hand side here. So we define something called phase margin and gain margin. So the phase margin is given by the distance of the actual phase to minus 180. So it's how far away we are from minus 180 at the frequency where the loop gain is equal to 1. So that's defined to be our phase margin right here. Our gain margin is defined to be at the frequency where the phase has gone to minus 180, what the gain difference is between the loop gain at that frequency and 0 dB. So how far below 0 dB we are. So that's our gain margin. Sorry. And if we notice, if we make our phase margin equal to 0, so if we say our phase margin is equal to 0, what that would mean is that our magnitude of L of j omega 1 is equal to 1, and the phase would be exactly equal to, at L of j omega 1 would be exactly equal to minus 180. In other words, that would mean that L of j omega 1 would be exactly equal to minus 1. So if 1 plus j omega 1 was equal to 0, this would occur because our L of j omega 1 is equal to minus 1. So 1 plus minus 1 is equal to 0. So our poles occur right on the j omega axis, and we'll have an oscillator. So that's why this phase is so important. In the case where our phase margin is equal to 0, it turns out that we'll have an oscillator. Our poles will be exactly, the real part of the poles will be exactly 0. If the phase margin becomes greater than 0, you can show then you have a stable poles. If the phase margin is less than 0, you'll have unstable poles. This is true under the condition that all our open loop poles and zeros are all on the real axis. So this is a requirement here that we, starting off with real axis poles and zeros in our open loop system, then we have a very simple method to look for whether our closed loop poles are either going to be stable or unstable by just looking at our phase margin. So there's a direct relationship between our phase margin and the stability of our closed loop system. Gain margin is used to indicate how much more gain we could add while keeping our system stable. Because if our gain margin increases, and we have 0 degrees, in this case here, again, if our phase margin was equal to 0, our gain margin would also equal 0. And so if we've increased our gain enough, we would also put our poles right on the j omega axis. So we generally are looking for phase margin, but our gain margin also tells us how much extra gain we can add in order to, before our system will start to go unstable. If we want to write some equations down for our phase margin, we can say our phase margin is equal to the actual loop gain angle, so the phase at j omega 1 minus negative 180 degrees. So in other words, it's the distance between here and here. So it's minus 180 because we have minus 180 over here. So that becomes our equation for our phase margin, which means you can also write that out as the phase plus 180 degrees. Our gain margin is equal to 0 dB minus our actual magnitude when the phase is equal to 180 degrees. In other words, it's equal to the distance 0 minus the actual magnitude of the loop gain at that frequency. So it becomes equal to just minus the magnitude of the loop gain in dB at j omega 180. And we'll see that the phase margin ends up giving us an indication of our closed loop settling behavior. So not only will the phase margin tell us whether we're stable or unstable, it'll give an indication of how much ringing we expect to occur. The lower the phase margin, the more ringing we expect to see. By the way, if we had a loop gain which was just a first order system, our phase margin would always be 90, and so we would have no ringing, and it would always be just a first order settling response. So it would just be an exponential curve. But it turns out if we have a second order system, then our phase margin would be less than 90. And if the phase margin is 45 degrees, you can show that the overshoot of the step response would be about 23%. In other words, if we had a step response here, so this is a step coming into our system, if the actual output looks something like this with some ringing to it, then if x is this amount where we're using 1 as our step value, our percent overshoot is equal to x divided by 100 in percent. So in other words, x would be 0.23 here, or 23%. So that's in the case where we have 45 degrees phase margin. So if we have 45 degrees phase margin, our step overshoot would be 0.23, or would be 23%. If we had a 55 degree phase margin, the percentage overshoot would be 13%. If we have 65 degree phase margin, the overshoot is only 4.7%. If you have 75 degree phase margin, the overshoot is only 0.01%, so it's quite a bit smaller than it is in the 45 degree case. So generally 45 degrees is not enough phase margin. What you find is most people will design, they typically want greater than a 60 degree phase margin for their circuit in order to have reasonable settling behavior. That ends this section. And we'll carry on in the next section looking at how to compensate and how to get a phase margin that we'd like to get. So given a system that is unstable, how can we modify it to make it stable with a given phase margin. Thanks for watching.